Hey guys, welcome to question MM248 of the Maths Methods Fortify study guide. In this question we've got a big inverted right circular cone which holds a smaller right circular cone inside it as shown in the diagram below. So we've got a big cone and then a flipped upside down cone inside it. The radius of the bigger cone is 6 meters and the height is 9 meters. The radius of the smaller cone is r meters and the height is h meters. Find h in terms of r. Awesome. So first things first is to recognize that we can create similar triangles out of this, right? So whenever we have two different shapes, especially when they're triangles, we want to try and create similar triangles out of that to make this easier for ourselves, or to make it even possible. Without doing that, we can't do it. So what we're actually going to do is we're going to create a triangle out of this big triangle here, and then we're also going to create a triangle here, okay? So whenever you do similar triangles, they have to be going the same way, like have the same ratio. Like we couldn't create a triangle here and then make this a similar triangle, right? Because it's not oriented the same way. It doesn't have necessarily the same angles. So we just need to make sure that we do that properly. So what we're going to say is that we have this big triangle here, which is from here to here. So we have our big triangle, which is 6 meters radius and 9 meters down. Cool. Now we're going to need to find this triangle here. Okay, so like I said, this is a smaller triangle, a smaller version of this triangle, right? Can you kind of see that? You can see that this big triangle here shrinks down to equal this, or not equal, but shrinks down to be similar to this small triangle here. So we need our height of this triangle, which is h, right? So from here to here is h, and that has the same height there. So a smaller triangle is going to be h, and then our other side length here is going to be, well, we know that this total here is 6. We know that this here is r, which means that this is also r. So this section here is 6 minus r, and that leaves this bit here. So it's 6 minus r. If you have any questions about that, hit me up in the comments below. I'm not going to go too depth into this without someone asking me. So if you do have a question, just plug it in the comments. So that's our first mark. So recognizing that we have similar triangles there is our first mark. What we're going to do now is, because these are similar, we know that they have the same ratio of side lengths, okay? Which means that one side length divided the other one is the same as this divided by this, okay? So 6 take r over h is equal to 6 over 9, which means that when we rearrange this, just going through the whole rearrangement process, we end up with h equals 9 take away 3r over 2. That's our second mark for this question, and our final answer for part A. If you have any trouble with this work solution, just check out the work solution sheet, and you'll be able to see what's going on. So let's move on to part B. Now part B is a 1-mark question, and asks us to find V, the volume of the smaller cone in terms of r. Awesome. So we're looking for the volume of the smaller cone, which is this one in here. Now we know that the volume of a cone is equal to 1/3 pi r squared h. And in this case, our r and h actually are r and h, which means we're going to get 1/3 times pi times r squared. But we're looking for our volume in terms of r, okay? So we have these values here, but we don't want this h, which is exactly why we found this first. So we know that h is equal to 9 take 3r over 2, which means we can replace h with that, right? So from here, we can expand this out to get 3 pi r squared minus pi r cubed over 2. That's our first mark, that's our volume, and that's it for question B. Let's move on to part C. Part C asks us to find the value of r for which V is at a maximum and state this maximum volume. So part C is a 3-mark question. We know that this is our volume, and we also know that if we're going to find V at a maximum, we're going to need to derive our volume and make it equal 0, okay? So whenever we have our maximum, as always, we're going to derive, which means that our dV/dr is equal to 6 pi r minus 3 pi r squared over 2. And like I said, in order to make the maximum volume occur, we're going to need to make our derivative equal 0, which means we get 0 equals 6 pi r, take 3 pi r squared over 2. That's your first mark. So recognizing that has to equal 0 is your first mark. We're going to take out a common factor of 3 pi r here. So we get 3 pi r inside of 2 take r on 2. which means we get 0 is equal to 3 pi r, or 0 is equal to 2 minus r on 2. So therefore, r equals 0, or r equals 4. Since our radius has to be greater than 0, because this radius can't be 0 or it wouldn't exist, so r is greater than 0, therefore r equals 4 meters. Yep, 4 meters. That's our second mark. So finding what our radius is, or our value of r, is equal to, it gives us our second mark. So that's our second mark. But now we actually also have to state our maximum volume. So we know that our volume is equal to 3 pi r squared minus pi r cubed over 2. And we know that our radius at a maximum volume is 4. So we can sub in 4 here. 3 pi times 4 squared minus pi times 4 cubed over 2. And this gives us 48 pi minus 32 pi, which gives us 16 pi meters cubed, which is our volume. And that gives us our third mark. And this is our final question and final answer for question MM248. That wraps that question up. Please let me know if you have any questions in the comments below. But otherwise, I'll see you in the next video, and thanks for watching.